Hello, welcome. This is Ajay. So, welcome to lectures on basics of radiation physics. So, in this lecture, I'm going to discuss basics of atom. My content is as follow. So, first, I will be discussing the neutrality of atom, then the line spectra of atom, and then different models given by different scientists. For example, the Thomson model, Rutherford model, Bohr's model, and their limitations. And at last, I will be discussing the de Broglie hypothesis. So electrical neutrality of atom. So atom as a whole is electrically neutral. So it contains equal amount of positive and negative charge. So let me concrete this by giving a real life example. So when you rub an object, or for example a plastic scale. So when you rub a plastic scale, what happens is it start attracting the pieces of paper. So the electrification has happened, something magic has happened. So what happened actually is, while rubbing, there's a transfer of charges taking place between the different atoms of different kinds. So due to this transfer of charges, the plastic scale become positively charged, so because it loses negative charge. So electrification happens just after rubbing. So before rubbing, there was no electrification. So in general, the atom as a whole was electrically neutral, was containing that material, or each atom was containing equal amount of positive and negative charge. So line spectrum of atom. So when you have group of atoms of some element, and when you excite them, so what happens is, like passing electricity or heating them. So what happens is they emit some radiation, and that radiation emitted by them forms a line spectrum. Only certain wavelengths are present in that emission spectrum. So most of the elements are stable and emit characteristic spectrum. So each atom has its characteristic spectrum. So line spectrum is actually a set of isolated parallel lines which depicts the wavelength that can be emitted or absorbed by that particular atom. So it just provides the useful information about the internal structure of the atom. So let me give you an experimental setup how we can see the line spectrum of an atom by doing an experiment. So this is an experimental setup. So this on the left side, I have a tube containing hydrogen gas which is being excited. So when it excites, it produces radiation. It produces radiation, and radiation is allowed to pass through a converging system, and that converging beam, after passing through the converging system, allows to fall on a prism, and that prism diverge the different components into different components depending on its wavelength. So we get a line spectra of the emission spectra, that the radiation emitted by the hydrogen gas. So this is an emission spectra, and this series corresponds to the Balmer series, like transition happening second uh, from the second n equals to 2. So this will be discussed later. So this is the uh, wavelengths that corresponds to Balmer series. So each atoms shows these line spectra. So scientists were worried with how, like, what is the structure of the atom actually. So how this line we are getting line spectra. So the scientists were worried about the internal structure of the atom. So many scientists came with a different model of the atom. So different models are the following. So first was the Thomson model, and the second was the Rutherford model, and the third was the Bohr's model, which was pretty successful model as regard to other two previous models. So the first model was given by Thomson just after the discovery of the electron in 1897. He came with the model of the atom, in which he proposed that an atom is a spherical cloud of positive charges, in which electrons are emitted inside it. So we can understand it with the analogy of the watermelon. So you can see this in image. So in this, the red fruit is actually the positive charge, and the black seeds are the electrons. So this was a simple model given by Thomson model. Thomson. just after the discovery of the electron. But there were some limitations, not some. It's totally a. So the first limitation was like proposed without any good experimental data. So there was no. He did any. He did any. He didn't perform any experiment to verify how is the what's what is inside in the atom. So it was without any experimental evidences, and it was also the failed to explain the stability of electron, how electron can reside with a positive charge, because like they should be repulsion actually, but how they can reside, though there was no explanation for such that for that for that. Uh, so and also the main thing was to explain the spectra line spectrum, because that was the first evidence we the experimental data that we have to explain, that any model should explain, but the Thomson model was not able to explain that also. So there was many limitations in Thomson model. So after Thomson, Rutherford came in. So in 1910, with his student, he did gold foil experiment with his student, and he proposed the model of the atom. So he, according to him, so most of the mass of the atom, and it's all positive charge, resides in a tiny space called nucleus, and the electrons revolve around that nucleus. So this is the experimental setup he did. He and his student did for the discovery of the for studying the structure, internal structure of the atom. So you can see a radioactive source which produces alpha particles, and the alpha particles are allowed to fall on a gold foil. And he observed that most of the alpha particles passes straight. There was no deviation, and there were few alpha particles that were deviated, and very few that were retrace their path. So from this experimental, he got the data and he gave the model. So according to him, the nucleus is positive charge. There's a tiny space in the atom, and electrons revolve around it. But there was limitation. So limitation were like it cannot explain the characteristic line spectra, which was the main data before. Like any model should at least explain this line spectra, but it wasn't his model wasn't able to explain this. And the second was like he contradicts his model contradicts the stability of the matter. So actually when so electron is actually revolving around the nucleus, so it's revolving, it's in circular motion, so it is accelerated around the nucleus in it. So since it's accelerated, so it should emit electromagnetic radiation. So hence it should be losing electromagnetic energy, and since it's losing electromagnetic energy, it should spiral inside or into the nucleus. Hence, uh, according to electromagnetic theory, the atom should not exist. But this is not the case. So there was a contradiction. So his model was not able to explain this contradiction. So this was a big contradiction. And later on, the Bohr came to explain. He came with his model. So inspired from the photon picture of electromagnetic radiation, Einstein photon picture of electromagnetic radiation, and the experimental evidences of the line spectrum of atom, the Bohr proposes the first semi-quantum model of the atom. So he gave three postulates for in his model. So the first postulate was like in an hydrogen atom, electron revolves in a certain stable orbits. So there are only some discrete orbits around the nucleus in which electron revolves, and in that discrete orbit or the stable orbit, the emission of radiation doesn't take place. There is no in that orbit, electron doesn't radiate energy. So those are a stable orbit. So in his second postulate, he stated that only those orbit exist uh, for which the angular momentum of the electron is integral multiple of h by 2 pi or h cross. In third postulate, he said like if a fourth electron transit from a high energy level, like from higher energy level E2 to a lower energy level E1, then there is emission of a photon having energy E2 minus E1. So h nu equals to E2 minus E1. So nu is equals to E2 minus E1 divided by h. So that is the frequency of photon that will be released when this is transition from higher energy level to lower energy level. So, using the classical physics and his quantization principle, he proposed that for a hydrogen atom, the radius of nth orbit is given by 0.53 into n square angstrom, where n is a principal quantum number taking value positive integer value. So one n can be 1, 2, 3, 4, 5 up to infinity, and the total energy of the electron in that particular principal orbit is given by minus 13.6 n square electron volt. So energy of the electron is inversely proportional to the principal quantum number, square of principal quantum number, and radius is uh, proportional to n square of the principal quantum number, like square of principal quantum number. So what is the ground state and excited state? So n equals to 1. The first orbit is said to be a ground state, and the ground state energy is minus 13.61 electron volt. If you put n equal to 1, you will get energy of the first orbit to be minus 13.6 electron volt, and the radius of that first orbit is 0.53 angstrom. So the orbits which is having principal quantum number greater than 1 are said to be the excited states. So any state having principal quantum number greater than 1 are excited states. And if atoms are excited to these higher state by a collision, so we, the electrons can be excited to these higher state. If suppose electron absorbs a photon of suitable energy, then it may excite to higher energy level. Or if two atoms have a collision, then by collision they may happen that electron may excite to higher energy level. So collision and by absorption of suitable photon of suitable frequency, uh, the excitation can be happen in an atom. So now coming to limitation of Bohr's model. So Bohr's model was applicable only to hydrogen atom, the atom having one electron. So just applicable to hydrogen or hydrogenic atoms. And the second was it cannot be extended a two electron system. So we cannot apply the Bohr's model to even to a two electron atoms such as helium. And also it was able to explain the line spectrum, but it was failed to explain the difference in intensities. Like some frequencies were having higher intensities, and was some wavelengths or frequency were having low intensity. So there was a change in intensity of different frequencies. So it wasn't able to explain that why this relative change in intensities of different frequencies. So by that time, many of the scientists were like, we have the evidences like uh, the light was showing both particle and wave behavior. So scientists were very much convinced with the dual nature of radiation. So light shows both particle and wave behavior. So inspired from this behavior, so so De Broglie proposed that nature loves symmetry. So since radiation, particle, the light which is showing both dual nature, so it must be that the, the matter itself should also show the wave behavior. So De Broglie in his PhD thesis proposed that uh, a particle wave is associated with a moving particle, which whose wavelength is given by h by mv, where h we all know is a Planck's constant, and m is the mass of the particle, and v is the velocity with which particle is moving. So this was his PhD thesis, and it was proved to be right by some certain experiment done after his hypothesis. So this hypothesis also helped in understanding the the Bohr's quantization rule. So we can understand the Bohr's quantization rule as follows. So only those exist for whose uh, the length of circumference is an integral multiple of the wavelength electron particle wavelength. So 2 pi r is the radius of the nth orbit must be equals to the n times the principal quantum number into the wavelength of the electron into the electron particle wavelength. So this is the pictorial representation. Like you can see, the electron is forming a standing wave in his orbit. So that number of standing waves should be the length of the total circular path. 2 pi r must be equals to the the wavelengths that standing wavelengths that are being formed in that orbit. So at last, let me thanks. So thanks for watching.